Hello, everyone, and thanks for joining us today. Firstly, I must apologise. You've only got me today. It's that time of year where people are on vacation. It's also a work day here in the UK. But yeah, we hope to be. Anyway, just thanks for joining me on this historic occasion. Uh, we basically what we're going to be watching today. It's something we've been talking about for years. It's been the years in the making. And this is the first light images of the Vera Rubin Observatory in Chile. Now, I know some of you are going to say, well, we've already seen some images because the the National Science Foundation and the US Department of Energy Office of Science have already issued two or three first light images already. And to be honest, they're absolutely stunning. But what we're going to do is we're just going to sit here. It should start in a little while now, in about 13 minutes. And what we're actually going to be looking at before we actually start is what is the actual Vera C. Rubin Observatory. First of all, let's have just a quick chat about who Vera C. Rubin was. Um, she was a female astronomer who, let me just find it, her work on the rotation of galaxies actually discovered that there was a discrepancy on what was actually predicted. Um, Basically, she was studying the rotation of galaxies and how fast they're actually rotating. And what she found is instead of they expected the outer stars to be moving slower than the inner stars because they're closer to the central black hole. But what she found is actually the stars on the outer, on the sort of like in the arms, on the outer limits of the galaxy, were moving as fast, if not slightly faster, than the stars on in the center. Now this went against all predictions, and basically it led to theorized the theory of dark matter, because for this to happen you need extra mass, and the mass of what in the galaxy of all the stars, the planets, etc., didn't add up. So this shouldn't have been happening. So to for this to happen, you needed extra mass, and this sort of like brought forward the theory of dark matter. Now, dark matter is a substance that does not react with light. It doesn't emit light, it doesn't absorb light, and it doesn't reflect light. The only reason we know it is there, it must have a mass because it is affecting the normal matter that is we are basically made up. It's what we're made up of. But for this to happen, it's quite a large proportion of the matter that we see in space um, makes up most of the matter. Um, and this is what the Vera Rubin is hoping to. Oh, excuse me, I've just lost my headphones. I've lost my paperwork. Sorry about this. Right, sorry. Let's try that again. So yes, the Vera Rubin. This is what is hopefully it's going to be studying. Now, the Vera Rubin, what it's going to be doing is every 3 nights, this huge telescope is going to be scanning the southern hemisphere skies every 3 nights. And then what it's going to do is it's going to take pictures every 30 to 40 seconds. The reason it's the exposure are that long, remember, it's looking into the deepest parts of space. And what it will be doing is it will then stitch these together into a time lapse. And it's going to be basically be a time lapse movie. So we're going to be able to, and remember, the universe is dynamic. Everything is moving. Everything's things. And to map these changes, you have to watch them over a period of time. It's called time domain astronomy. We can actually see these events happening. It's going to be looking for things like transient stars, stars moving between galaxy in the galactic space. It's going to be looking for also black holes moving between in the intergalactic space that are just sat there and we can't see them. And it's going to be looking at things like supernova, things that actually happen, and we can see them actually happening in the time that we're actually looking at it. Now, this survey is going to be 10 years long. So this is going to basically be a 10-year movie of the southern skies, and it's going to be mapping the but basically it's going to produce a map of how the structure of the universe. It's going to give us an idea where the dark matter is hiding. It's also going to be looking at the expansion of the universe, because as we know, the expansion is moving, and it's being driven by the expansion is happening, and it's being driven by dark energy. It's basically going to be looking at the dark side, if you want to put it that way. It's going to be looking at the dark universe, the stuff that we can't see and we can't detect, and what effects they're having. And by looking at basically a structure of how everything, all the matter that we can see and we can measure, is actually formed into the galaxy, the structure. We've got what we call the cosmic web. And by looking at that, we'll be able to hopefully understand more what dark matter and dark energy are actually doing to our universe. And as I said, this is going to be happening for 10 years. Now, the Vera Rubin telescope, as I said, is when it's been built, how are they going to map this thing? Well, they're using the biggest camera ever built. And when I say this camera is big, during the run up, we were saying it's the size of a largish car. But when we saw it actually being installed, I would say it's actually more a Ford Transit van size. It's absolutely huge. It's also got the um, biggest sensor ever made, because you're going to have to catch as much light as possible when you're looking into this deeper regions of the universe. It's going to be looking at things within our own galaxy, the Milky Way, and that hopefully this is going to give us a far more understanding of what's actually going on. I mean, it's also going to be looking at things like failed stars, what we call brain dwarfs. These are stars where the gas has collapsed to actually form a sphere of gas under pressure. Now, if they get big enough, they will ignite and actually form a star. But of course, sometimes they don't get big enough, and sometimes a little bit of nuclear fusion will start, but it will stop because there's not enough gas or pressure there. And these form what we call brown dwarfs. Now, they're hard to detect, but with the Vera Rubin, with her cameras and her what they'll be using, they will be able to detect the very dim light these things do actually emit. So it's really exciting. The last time we had anything like this was with the James Webb. Um, if you remember, that was back in, I think it was 1922, was it? Um, when we saw the first light from there, and the images again were absolutely stunning. The Hubble was another one, and of course we've got with those, but with those they are actually space-based telescopes, whereas Vera Rubin is terrestrial. It's actually on the Earth's surface, and it's actually down in Chile, because that's where this seems to be where the best skies are. I'm just trying to sort my paperwork because it all fell on the floor. It's I think it's Mount Machion, in Chile, that it's actually been built on. And of course, to build this machine, they had to basically flatten the top of the mountain. So we've been looking forward to this. It was they were hoping first light was going to be in 2024. But unfortunately, with COVID and other things that have happened in the last few years, it's been delayed. It's like everything in life; it's been well delayed. So we've been looking forward to this. If you've been fortunate enough, you've probably seen the images that they've already released. They're promising to show us more images, which is why we're still going ahead with this show, because it would have been pointless if they showed all the images in one go. But the images, if you've seen them before, are absolutely stunning, absolutely fantastic. So anyway, as I said, welcome again to this show, and hopefully, well, unfortunately, you draw the short straw. You've got me, the blithering idiot who drops his paperwork everywhere, and now has got to sit down and sort it out. But yes, this is going to hopefully answer lots, or at least give us a better understanding of how the universe was formed, how it's expanding. Because as I was talking about dark energy, that is responsible for the expansion of the universe, and that seemed to be increasing. But recent studies have actually said now that possibly this expansion that was increasing seems to be now slowing down, which means because of course nobody knows how the universe is going. If it carries on expanding, there's the we would see basically become very isolated and very lonely, because all the galaxies and all the stars will be moving away from us, and eventually they'll be too far away for us to be able to see. And the theory is that at the end of the day, one of the theories was, I don't lose any sleep over this, was that eventually it expands so much that the actual fabric of the universe would tear. It's called the Great Tear, and everything will blink out within seconds. But if it is slowing down, that means possibly that it will go into reverse, and maybe it will all start to shrink down again, which is another theory of how the universe will end itself. And then, of course, there is a third theory, which is called the cold death, where basically we use all the hydrogen in the stars, and everything will eventually just blink out. So everything will go out. So anyway, we're getting close to the start of the presentation. Um, Basically, once it comes on, I may have to occasionally cut the sound if they start to play music, because then we'll fall foul of copyright rules. But hopefully they're going to, once they got through the start, there probably will be a build up, and we'll explain, and hopefully there'll be some videos showing what the Vera C. Rubin um, is all about. I mean, it's also known as the LSST, which also means the Legacy Survey of Space and Time, which is LSST. And this is what the uh, observatory is also known as. And as I said, it's studying time domain. It's going to be looking at how everything is moving, um, how and hopefully answer why certain things are traveling through intergalactic space, um, and how dark matter is the dark side is actually uh, affecting all the matter it is. I mean, the thing is, the dark side, the dark matter, it actually forms most the dark matter, and dark energy actually forms most of the matter in the universe, with only 5% of it actually being baryonic matter, which is what we're made up of. So yeah, it's just hopefully going to be an amazing instrument to to so. I mean, in the moment, our common theory, most best theory is matter makes up 5% of the stuff in the universe. Then dark matter 27%, followed by dark energy, which is 68%. And we've got to really sort of like we would just like to know and hope find out and understand how this is affecting the universe, and why the universe is expanding. So it looks like we're just about to start. They're just waiting um, for national science. So what we'll do is as soon as we see any action, we will move over and we'll go and have a look and see what they're actually talking about. But this has been an exciting time. As I said, the last time we did this was with the James Webb. And the James Webb has just absolutely blown everyone away. It's completely messed with people's heads about the theory of the Big Bang, as we thought. It's sort of like meddling with sort of possibly the age of the actual universe, because we think it's around 13.8 billion years. But what we're seeing in the furthest distance in time, because this is when you're looking at light, you're looking at time, and the further away it is, it takes longer to reach us, and it gets what we call redshifted. But that's for another story. So at the end of the day, looking back, we're finding that we had black holes, we had huge galaxies really back when they shouldn't have been there, according to our current theories. So again, we've got to, again, with the Vera Rubin, hopefully we can answer some of these questions. Why these things have not, why things have happened as they are? Because I mean, with the expansion of the universe, of course, we basically the expansion seemed to be quite even to begin with, and then about, I think it was about 7 billion years ago or something like that, it went through what we call a phase change, where all of a sudden it started to expand faster and faster and faster. Why did that happen? Why did the dark energy start to increase, which is, of course, as I said, is making the universe actually expand. So yes, I mean, hopefully this will answer a lot of questions. Today we're going to be looking at some pictures, and as I've said, if you've been lucky enough to capture the pictures that are in the news since this morning, they are absolutely stunning. The clarity, the detail that we're seeing, and of course, as I said, this is looking a lot deeper into the universe. And what we're waiting for is, to be able to study these. In fact, I mean, some of the images I've seen are so full of galaxies, it's so far back in the distance that it is absolutely amazing. It's just like a cloud of stuff. Well, we seem to be starting, so let's just go over and have a look. As I said, I may have to mute. So let me just just going. Here we go. Okay, no sound.
Brian Stone.
Well, thank you, Ed, and thank you to all of you for being here today. Starting today, our ability to understand dark matter, dark energy, and planetary defense will grow even faster than ever before. This exciting new future is thanks to the vision, work, and support of the many people we're proud to recognize here today. Let me begin by thanking the White House Office of Science and Technology Policy Director, Michael Kratsios, and the administration for their continued support of exploratory science. By working across federal agencies, OSTP, NSF, DOE, we turned shared investment and coordination into a transformative interagency public-private partnership. The flagship observatory has been more than 20 years in the making, with NSF behind the project every step. NSF brought together a coalition of partners to build and support the cutting-edge facility, instrument, and data management systems. More than 40 international organizations contributed to building Survey Telescope with the ability to gather more data than all other ground and space-based optical telescopes in history combined. NSF is proud to continue to lead Rubin's operations as it begins to deliver on its promise to expand our understanding of the universe. Thank you to DOE, our international partners in Chile, private donors like Charles Simoni, the National Academies for prioritizing Rubin and the 2010 Astronomy and Astrophysics Decadal Survey, and the entire Rubin team, especially Tony Tyson, Rubin LSST chief scientist who conceived and championed this project from the start. Vera Rubin is the namesake of this facility because she is the symbol of scientific excellence. Her legacy reshaped astrophysics and our understanding of dark matter. Generations of researchers have been and will continue to be inspired by her. Alan Rubin, one of Vera's children who's joining us here virtually today, once told NSF, Vera believed there is always more to be discovered. So let's keep discovering together and proving her right. Now I hand it off to Kathy Turner from the Department of Energy. Thank you.
Hello, everybody. We're incredibly thrilled to be here today for the unveiling of these new images from the groundbreaking NSF DOE Vera C. Rubin Observatory. Just a preview of the data to come. I'm Kathy Turner, Program Manager for Rubin Observatory from the Department of Energy Office of Science. Carrying out this project in partnership with NSF and the private and international partners has enabled us to bring all of our strengths to this amazing observatory. I am honored to work with all of them and look forward to our continued partnership. This observatory represents a giant leap in our ability to explore the cosmos and unwrap the mysteries of the universe. Of great interest also to the observatory's namesake, Dr. Rubin. Now I'd like to introduce Harriet Kung, our Acting Director of the Office of Science at Department of Energy. With decades of experience in scientific leadership, her vision and dedication have been instrumental in making this amazing observatory a reality. Please welcome Dr. Kung.
Good morning, everyone. Thank you, Kathy, for the wonderful introduction. On behalf of the U.S. Department of Energy, let me add my thanks to the long list of organizations that has made today's event possible. First of all, National Academies. I would especially like to single out the Board on Physics and Astronomy and also the Space Studies Board for hosting us in this beautiful auditorium today. I also want to thank White House OSTP, the National Science Foundation, and also the Association of Universities for Research in Astronomy, as well as my colleagues in DOE's Office of Science for putting together the wonderful program that we'll witness today. But let me first introduce a short video from the Secretary of Energy, Chris Wright, who is not able to join us today, but he took the time during his recent visit to SLAC National Accelerator Laboratory to film the video you'll be seeing shortly. So let's cue the video.
Today we celebrate the culmination of 2 decades of scientific and technological innovation that have given us an ability to look into the cosmos, to understand our universe itself. This is the Vera Rubin telescope in Chile, and I want to congratulate all of those at the Department of Energy and the National Science Foundation, those working at SLAC out here in California, where I'm standing right now, and those on the ground in Chile, for this tremendous technological achievement that truly will bring an understanding of our universe simply not possible before. The movie has started, the camera is running, and we're going to see our cosmos unfold before us. Congrats to all.
Thank you, Secretary Wright. Having this event today really feels like a homecoming. It was really the 2010 National Academy's Decadal Study for Astronomy and Astrophysics that recommended that our high-energy physics program partner with NSF on what would become the Rubin Observatory, which was the number one top-ranked ground-based project. As Brian has already mentioned, the NSF DOE Vera Rubin Observatory was a project long in the making with many moving parts. The DOE's Office of Science was proud to lead the construction of the LSST cam, the largest digital camera ever built. It is the size of a small car, but twice as heavy. The camera, boasting an impressive 3,200 megapixel resolution, was lovingly designed and fabricated by scientists and engineers at SLAC National Accelerator Laboratory, with critical contributions from DOE other national laboratories, as well as international partners. This camera, in conjunction with the Smithsonian Survey Telescope, will create a 10-year survey of the sky in the Southern Hemisphere, known as the Legacy Surveys of Space and Time. This treasure trove of data set will give researchers unprecedented depth and clarity to questions that drive the fundamental research supported by DOE's Office of Science. And some of the questions include, how can we better understand the matter and energy that makes up 95% of our universe? And why is our universe ever expanding quickly, and how is that pattern change over time? And also, what role did dark matter play in how our universe evolved? We anticipate that the observatory will give us many insights into our past, our future, and possibly the fate of the universe. Answering these questions is a challenge that is matched with the many, many talents that contributed to today's success in the survey. And we at DOE are extremely proud of the many people that have contributed to this amazing project. We're especially grateful for the indispensable cooperations from our international partners. In particular, the success of the Rubin Observatory relies on its location high atop Cerro Pichon in northern central Chile. That's why I'm so pleased to introduce to you His Excellency, the Ambassador of Chile to the United States. Ambassador Juan Gabriel Valdez has dedicated his career to fostering strong ties between our nations. Please join me in welcoming Ambassador Valdez. Thank you.
Good morning, everyone. Mr. Michael Kratsios, Director of the White House Office of Science and Technology Policy. Mrs. Harriet Kang, Acting Director of the Office of Science at the Department of Energy. Mr. Brian Stone, performing the duties of the Director of the National Science Foundation. Distinguished American and international authorities, esteemed scientists and friends of the National Academy of Science who welcome us today. I'm very happy to be here today. I have to say that I have received a number of calls from our friends, astronomers in Chile, saying that I had to be here today. Therefore, it's a fortune to be representing them this morning. Chile is without a doubt an astronomical nation. Evidence of astronomical observation by our earliest inhabitants dates back more than 2,000 years before Christ. Our geography gives us clear, dry, and stable, ideal skies for observing the stars. Astronomy is part of our identity and our heritage, and we are proud of it. But it is not only nature that has led us to become global leaders in astronomical observation. It is also the result of our government decision, a clear and sustained policy of international cooperation, scientific development, and the protection of our dark skies. Today we celebrate the first images from an extraordinary telescope, the Vera Rubin Observatory, equipped with the largest digital camera ever built for astronomy. But we also honor the memory of an extraordinary woman. Vera Rubin was not only a pioneer who uncovered key evidence of dark matter, she was also an inspiring example of integrity, perseverance, and humanity. Vera Rubin pushed the boundaries of scientific knowledge, but also her era. Naming this observatory after her is a profoundly symbolic and just act. It sends a message to new generations, and especially to the children and young people of Chile and the world, that knowledge has no gender and that the university is open to all. Vera Rubin has been the inspiration for the important and growing number of women astronomers we have in our country. For Chile, the observatories represents our commitment to knowledge, to sustainable development, to international cooperation, and to the defense of dark skies. The Vera Rubin Observatory is part of a unique ecosystem. Today, more than 40% of the world astronomical observation takes place in Chilean soil, and by 2030, that number will exceed 55%. This also places a great responsibility on us to protect our skies, to support science, and ensure that the knowledge generated here benefits all of humanity. Finally, I would like to thank everyone who made this project possible and who placed their trust in Chile as a strategic partner, the institutions of the United States government, especially the Department of Energy and the National Science Foundation, the international consortium led by Aura, the universities, engineers, technicians, and local communities that participate in this process, and to all who dream of uncovering the mysteries of the universe. We are delighted that the United States is looking at the universe from Chile. Thank you very much. I now invite Dr. Harriet Kang, the Acting Director of the Office of Sciences at the Department of Energy, to address us. Thank you very much.
It is now my distinct honor and privilege to introduce Michael Kratio, Director of the White House Office of Science and Technology Policy and Assistant to the President for Science and Technology. Director Kratio previously served as Chief Technology Officer of the United States during President Trump's first term, where he advised the President on landmark initiatives in artificial intelligence, 5G, quantum computing, and advanced manufacturing. Looking back, many of these initiatives not only had launched, but have continued to shape the trajectory of the nation's science and technology. Today, he continues to advise the President on emerging technologies and helps drive America's leadership in critical sector vital to our national strength. Please join me in welcoming Director Kratio as we mark yet another milestone in America's golden age of science and technological greatness. Welcome, Dr. Kratio.
I'd just like to say thank you for sticking with us. They're going through the preliminaries at the moment, and hopefully very soon we'll be
Good
seeing
morning
some
to
very
everyone
nice
here
pictures.
and watching online. Thank you, Dr. Kung, for that introduction, and thank you all for joining us as we celebrate the completion of a monument to American leadership in fundamental science. The American people have always been animated by a spirit of exploration and our national story is one of pioneers seeking new horizons and endless frontiers. It is fitting then that with the construction of the NSF DOE Vera C. Rubin Observatory, we will once again see further into space and deeper into time than ever before or anyone else. These first exquisite images made public today remind us of the full meaning of the words like awe and wonder and the limits of our language. They are sublime in their beauty, overwhelming in their scope, and profound in their promise of a discoveries to come. Like the majestic Hagia Sophia, with its soaring golden dome and glowing mosaics, lifting the spirit towards the divine, the Rubin Observatory draws our eyes and our hearts upwards to the heavens. Long before Aristotle demonstrated that the earth was round, and even before Abraham looked up at the stars and saw the promise of God, humanity has peered into the skies in reverence, seeking to understand our place in the cosmos. We believe the work of this observatory will help us find long-sought answers and ask new and better questions. It will also provide the best map mankind has yet made of our region of the universe. From the Lewis and Clark expedition to the Voyager probe and the Hubble launch, America's greatest efforts into the unknown have been public goods supported by the far-sighted leaders in government. Some projects are just too big, too genuinely monumental for any other institution to take on. Only we, the people of the United States, can do it. In its primary mission, executing the legacy survey of space and time, the Rubin Observatory is a joint initiative of the National Science Foundation and the Department of Energy's Office of Science. It represents a whole-of-government effort, a magnificent partnership of the many components of the federal research ecosystem, demonstrating our shared work at its best. Let me extend my thanks to everyone whose efforts have brought us to this day, including Brian Stone, Harriet Kung, and Ambassador Valdez. We know that the best environment for truly groundbreaking basic research is collaborative and interdisciplinary. Thanks especially to the scientists of the National Science Foundation's National Optical Infrared Astronomy Research Laboratory, under the management of the Association of Universities for Research and Astronomy, and DOE's partners at the SLAC National Accelerator Laboratory. Each part of the national research enterprise has their role to play in this truly magnificent work. The telescope at the Rubin Observatory is a triumph of American technological ingenuity and skill. Its 27.5-foot mirror combines the primary and tertiary mirrors into one surface and was manufactured over the course of 7 years at the Richard F. Karras Mirror Lab at the University of Arizona. The 6,000-pound digital camera is the largest ever made, the size of a car, custom built by SLAC with a 3,200 megapixel CCD array and 9.6 square degree field of view. That means it could take a picture of 45 full moons at a resolution so high it will need a wall of 400 ultra-high definition televisions to show it at full size. The 20 terabytes of data produced a day will be transferred to SLAC minute by minute for initial processing and distribution. With its unique mirrors, unrivaled camera, and trailblazing AI computing infrastructure, the observatory represents an investment by all of us in the future. Ours is a country of beginnings, of projects, of designs and expectations, too many of which have been borrowing from posterity for the comfort of the present. The project is, instead of a burden of debt, a gift to our children, one of which will lay down a cornerstone of knowledge and basic research today on which they will proudly build tomorrow. All of our most extraordinary technological advances and increases in our awareness have rested on new paradigms in fundamental science, as our brightest minds have groped closer to the truth of things and uncovered the mysteries of creation. In their knowledge of our ignorance, scientists like Vera C. Rubin have named two of those mysteries dark matter and dark energy. And we all hope that with the help of the Rubin Observatory, these hidden cosmic neighbors will eventually uncover themselves to human science. In the meantime, I trust that the stunning images and staggering amount of data the observatory will produce will support exceptional scientific efforts around the world. The United States remains at the forefront of international science and technology research efforts, a leader whose partnership is always wanted. More importantly, even more than that, I hope the observatory and its work inspires America's children with awe and wonder at the grandeur of the cosmos and causes them to fall in love with the sciences and mathematics. So congratulations to everyone whose leadership and hard work made today possible. Your nation is proud of you and very proud of this observatory. And thank you all for joining us as we celebrate this achievement. And now, for the reason we are all actually here, let's see some of these amazing images.
So this is what
You
we've
can
been waiting
plan,
for.
but sometimes things don't go as planned. We were hoping that Director Kratsios would show you first image. This observatory is the greatest astronomical discovery machine ever built. And we finally started working with it. This is the first image that we are unveiling to the whole world today. Thank you for your reaction. But now that we looked at this image, I have to reveal a fun fact. This image actually shows only a small portion of one Rubin image, just about 2%. In other words, the entire Rubin image is 50 times larger than what we are seeing here on the screen. So you may wonder, why didn't we show the entire image? Let us see why. Rubin Observatory, including its Simoni survey telescope in the middle, LSST camera on the left, and an exquisite software framework, is designed to make huge images rapidly. These three components you can see on the screen and their technological breakthroughs is what makes Rubin and LSST possible. Let us first have a quick look at the super agile Simoni survey telescope in the middle. You will notice the color scheme is matching everywhere, and indeed, my official Rubin tie is modeled after the telescope. Here you can see Simoni survey telescope inside the observatory's dome. The point of this short video is to demonstrate the amazing ability and agility of this 300-ton telescope. No other large telescope in the world can move this fast. It moves around in seconds. Other large telescopes take minutes. Let us now look quickly at the LSST camera. This big, beautiful camera is already in the Guinness Book of Records as the largest astronomical camera ever made. It makes huge images. As we just heard, just one Rubin image covers sky area equal to 45 full moons with its 3,200 megapixels. But that many pixels makes it very hard to display such an image. This is more pixels than the human eyes, your eyes, my eyes, can see. And this is the main reason why we could not show you the entire image right away, but only this small image shown in the bottom right. You can see its relative size to the full field of view in this small rectangle at the bottom. As Director Grazios pointed out, we would need 400 high-definition televisions to properly display just one Rubin image so that your eyes could capture all the detail. That means covering a basketball court with 400 TVs to display just one image so that your eyes can see all the detail. But instead of looking at 400 TV screens or walking around a basketball court, our team has developed a powerful web display tool that we can use to move around our giant images. We can zoom in and zoom out. We can explore and admire details of any object you choose to look at. Next, we will look at a region of sky about twice as large as one Rubin image. It is centered on the giant elliptical galaxy called Messier 49. This region that we'll explore in a second is about 100 times as large as the first image we saw today. The follow video is 1 minute long, and we will first enjoy it without any comments. Then we will replay it and I will comment. Enjoy. We will look at it again. Before we start, I want to say that the entire Rubin team is so excited about this data. We have been talking about this data for over 2 decades. It's finally here. Let's look at it again. Please pause. You can see here a universe teeming with stars and galaxies. The seemingly empty black pockets of space between stars in the night sky, when you look at it with unaided eyes, are transformed here into these glittering tapestries. There is barely a pixel in this image that doesn't have some light coming out. And only Rubin can produce quickly such large images with this much color and richness. Please continue. Play. You can see spiral galaxies, elliptical galaxies, clusters of galaxies. Please pause here. This is an amazing region. We need to stop here. I love it. Do you love it? Yes. Everybody loves it. Here you can see a stunning variety of celestial objects, from bright stars in our galaxy, ranging in colors from blue to red, to these nearby blue spiral galaxies, to more distant elliptical galaxies that are yellow and red in color. You can see how vividly these colors are, and that's very important for science. Colors of galaxies are very important because using these colors, we estimate distances to these galaxies. You can also note in this image that galaxies are not randomly distributed in it, but they are clumped. They show clumping and statistical details of that clumping, and distances to these galaxies determined from LSST colors will enable very precise, unprecedentedly precise studies of the expansion history of the universe and studies of dark matter and dark energy. That's what we measure, where these galaxies are, how big they are, and what are their colors. And in few years, LSST will be producing unprecedented cosmological results. Let's continue. And now you can see the full extent of that image. It's about 2 LSST or Rubin fields of view. And this is how we scan the sky, 30 seconds per exposure. There were about 10 million galaxies, close to 10 million in that image. Thank you. This slide shows again the whole area that we just looked at the end of video, with the first image from today outlined in the top left corner, that small portion where your eyes could tell the detail. Known objects here are annotated with their names, and you may notice that most faint objects do not have their names shown, and that's because they have not been studied before. Most of these objects have never been seen by people before. As we already discussed it, in this projection, you simply cannot see all the details in this image because our human eyes and our screens are not good enough and large enough. There is so much more in this image that you can enjoy, that you could see in that 1-minute video. And you can actually do it yourself later at home using our tool that we developed for this purpose. All you need is internet, and at the end of the presentation, I'll give you a QR code with a link. And now I'm talking to our colleagues and friends on the internet watching us through YouTube. At the end of the presentation, you will get a link, and then you can spend the rest of your day enjoying these 10 million galaxies. We hope you enjoyed it, but there is more to show you today, much more. Imagine now an image like what we just looked at, but imagine it 1,000 times larger. That would be half of the sky, or the entire sky visible from Chile. That 1,000 times larger image than this giant image we just looked at, this is LSST, Rubin's main goal for the next 10 years. But LSST will be so much more than just an image, even though such great large image, it will be so much more than just an image. And that is because every object included in LSST, about 40 billion of them, for the first time more celestial objects than living people on Earth. Every object will be imaged about 800 times during these 10 years that it will take to deliver LSST. And that brings us to the greatest movie of all time, LSST. Because we will have 800 different observations, we can take these frames, we can put them in a movie, a digital color movie of the night sky. As I said, Rubin Observatory is the greatest astronomical discovery machine ever built. So let's see quickly what makes it so uniquely powerful. Most importantly, it can scan the sky super fast, about 10 to 100 times faster than any other large telescope. This is like comparing the speed of your car to the speed of an airplane. That's what we are doing. Instead of driving around from east to west coast for many days, we pop on a plane and we are there in 5 hours. That's what we are introducing here. It took us a few nights to collect data we are showcasing today. With existing facilities before Rubin, it would have taken at least a year and maybe more. And LSST would take 1,000 years, which is obviously impractical, not 10 years. This is why we had to build Rubin Observatory. And so let's talk now a little bit about movies. We have a couple of trailers to show you. So objects, we make movies of the night sky to see two things, objects that move and objects that change brightness. So objects that move come in two flavors. Stars in our galaxy move, and they move slow. We detect it, but it's slow. Much faster objects are asteroids, and they are in our solar system. And so we'll focus now on asteroids that we discovered in those few nights of data. So here, nothing is moving yet. This is just to show you a tiny portion of that image that we will zoom in to discuss asteroids. Nothing is moving here either. What you can see is two spiral galaxies. What you cannot see is that these two beautiful galaxies were photobombed by asteroids. Let us see how. Here you can see asteroids as colored streaks. They are not satellites. They are asteroids that move during exposure. And this color image is made by combining many individual exposures. But asteroids, because they move, they disappear after you got one picture of them, one exposure. So these colors correspond to the principal colors used to construct color image. So you have red, you have green, you have blue. And so these asteroids, when we combine the image, we can remove them. Our software is smart enough to recognize them and remove the streaks when combining individual images. This is why you did not see them before. But now we will focus on asteroids. It's another 1-minute video. It showcases our unprecedented ability to detect small objects orbiting the sun. You can see motion against the static background of stars and galaxies. And we are only showing asteroids discovered by Rubin, not previously known asteroids. These are all new discoveries that were reported to the Minor Planet Center at Harvard this morning. There are so many of them. Just a few nights of data, just one tiny region on the sky. And now you will see their location in solar system. Let's pause here. So this blue donut, this is simulation of all the asteroids we expect there. And because we only spent few nights to get these data and we looked towards one small region on the sky, all of these new discoveries are found in this one narrow slice of this big donut. In 2 or 3 years, after we start LSST later this year, we will sweep around and discover all of these millions of asteroids. So we had 2,000 in these few nights of data. There are 7 near-Earth objects that have orbits that cross Earth's orbit. None of them is in such position to strike Earth, don't worry. We'll get tens of thousands more near-Earth objects. And we will discover about 5 million new asteroids during the next few years with LSST. This is 5 times more than all the astronomers in the world discovered during last 200 years since the discovery of the first asteroid. So because of this rapid development of technology today, we can outdo all these 2 centuries of effort in just a couple of years. Let us now see another illustration of the ever-changing night sky. We will look at objects that change their brightness. They don't move, but they change the way they look. We will look at stars that are called variable stars because they vary in brightness. They can change brightness on timescales from minutes to years. And by the end of LSST, we'll have data we will know of about few 100 million variable stars. This is mind-boggling to people who work in this field. LSST will also discover a few million supernovae. Supernovae are exploding, dying stars that are very important for cosmology because it's relatively easy to estimate their distance. We will now take a detailed look at a few variable stars called Ara Lyrae. They can become twice as bright in only few minutes, half an hour. That's why we chose them for this presentation. They are in reality about 50 times more luminous than our sun. And they change brightness because the whole star is pulsating like this on time scale of some hours. They are also very useful for studying dark matter in our galaxy because we can get their distances easily too. Here you see this blue star. It's blue because it's hotter than our sun. Our sun would look yellow in this image. And here we are comparing its brightness. Please pause here. So what you can see is color image of that star, average color image, and these two observations show its brightness in individual images. And the one in the middle is 30% brighter than the one on your right. It is hard to tell with your eyes, but it is very easily measurable in our high-quality images with our high-quality software that goes through those images. Let's continue. We'll see a few more Ara Lyrae. The next example is even harder to tell with your eyes. It's only 11%. But again, for our powerful, precise software that looks at it, we know it's 11% and not 10 or 12. All these stars are found in our home galaxy, the Milky Way. It's easy to get their distance. To distances much further than we can do today. And so over the next few years, we will map the distribution in the outskirts of our galaxy of both stars and dark matter more precisely than ever before. As you can see, the strength of Rubin and LSST is in huge images, in fast scanning of night sky, in discovery of huge samples of billions of celestial sources, and in studies of those sources with time, how they vary with time, do they move, do they change brightness? And that is the real purpose why we built Rubin Observatory. But there is one more thing to tell you today. As we look at the sky, we don't only collect huge samples, we make images of beautiful objects. And so today we want to share with you few beautiful objects, and we chose the Trifid and Lagoon nebulae. These nebulae are giant clouds of gas and dust, and they represent stellar nurseries. They are places in our galaxy where new baby stars are born by those clouds collapsing and becoming hotter and denser until you end up with a protostar, with a young star in the center. So this is the whole image. There are two nebulae. Top right is the Trifid Nebula. This pink nebula in the bottom is called the Lagoon Nebula. Again, this image is very large. It's about as large as the entire Rubin image. And your eyes and our screen are not good enough to display all the detail that we recorded in that region. Again, we will show through video that zooms in around all the vivid detail that is captured in that image. So, ready? Warp 1, engage. Wrong video. How did that happen? Peculiar. Huh. All right. We will have to leave that for later. So let me say a few words about what's next for us. That video, by the way, you can see when you follow the link from before, so nothing much is lost. You can enjoy it later. So we've just seen mesmerizing treasure trove of the stuff that LSST will start producing. We are getting to the close of the construction project. We are not done yet. We have some commissioning work to complete, some verification work to complete, but in a few months we expect the project to be completed. We go into operations, and we will start this greatest digital movie of the night sky later this year, and it will go for 10 years. We did not talk today much about science, but I do want to mention over 2,000 LSST scientists who are eagerly awaiting the start of LSST survey. We want to thank them today, thank them for helping us to arrive to this point with their support and expertise. They helped us first build the science case for LSST that led to LSST being ranked #1 in NAS Decadal Survey in 2010, and they also are helping us to build Rubin Observatory. They are organized in 8 topical science collaborations, and they greatly benefit from the supporting nonprofit organization called LSST Discovery Alliance. It's formerly known as LSST Corporation, and that is the organization that started this project. But I also want to emphasize it is not just the scientists who will enjoy LSST data, it is everyone with curious mind interested in what's up there, every child in school. We will have tools and materials that our education and public outreach team produced that you can use to be citizen scientists, that you can see in videos in planetaria, that if you're a teacher in high schools, it maps on your science curriculum. All of these will be available from that link QR code in this slide. And so now I will finally finish this brief presentation. The entire Rubin team, and let me add that I was greatly honored by our Rubin team to represent us today. The entire Rubin team hopes that you enjoyed this presentation. Please stay tuned for the exciting discoveries expected from LSST over the next 10 years and beyond. Thank you all here. Thank you all who are watching us over internet. Hundreds of locations in the US and Chile. Thank you and muchas gracias. Thank you to several hundred, close to 300 other locations around the globe. Hvala svima. And thank you for being with us today. And a big thank you to SLAC and Aura, our managing organizations. Heartfelt thank to our funding agencies, NSF and DOE, to our awesome program officers, Dr. Eda Jar, Dr. Kathy Turner, thank you, thank you, thank you. And finally, we are all very grateful to our host today, the US National Academies of Science. Thank you for having us. Greetings to all from the Rubin team. Thank you.
Wow.
Well, what do you think of that then, Michael?
Oh, absolutely amazing. I saw those main images on the 1 o'clock news at lunchtime, and even on normal television, they look amazing.
Yeah, I mean it's I'm just sort of stunned in what they did with just the test data. It's amazing. All those asteroids they found.
Oh God, yeah, you know.
Yeah, and I mean able to detect the light variations in variables, and again, like you, I have seen the images.
Yeah.
In fact, actually, I'm just going to pop back to it because it looks like they're showing it.
Oh, is this the glide through?
Yeah, it looks like they've actually decided that they're going to show it. Let me just get back to it.
Yeah.
I mean, the detail in this alone, I mean, this is what they've been showing.
Number of stars. I mean, is that the Trifid or is that the?
I think it's the Rosetta.
Oh, right.
Oh, look, an emu.
Yeah.
It's absolutely. Oh, wait, no, it might be the Trifid. Yeah.
Oh, yeah.
But the actual, yeah, it's a Trifid. But the detail in it is absolutely amazing.
I know.
I mean, the clarity. I mean, when he listed, he put up the full image. It's just a mist because there's so many stars and so many uh, galaxies. Well, they're not stars; they're galaxies.
Oh yeah.
Because you're not going to see individual stars. I mean, when you look at the images, you see these bright white stars.
Yeah, that's
Well,
right.
well, that's the stars that are closest to us.
Yeah,
They're
yeah,
between us and the image. We can see them.
yeah.
They're in our own galaxy.
Right.
But beyond, it's just an absolute mist. In
Yeah.
every single dot, pixel is in a pixel is
Yeah.
a galaxy. I'm just absolutely blown away. I can't wait to see
Yeah.
some real data once it starts coming through.
If you think, yeah, if you think we knew the universe, just wait for this.
Yeah, I mean the thing is what was it they said they reckon they're going to show 8 billion. Sorry, let me just get this right. I don't want to mess it up. Oh, you weren't with me. I dropped all my notes right at the very beginning.
Obviously.
Bit of a nightmare.
Yeah.
But I think it's something like there's going to be 800. But this is the southern hemisphere.
Oh no.
And yeah, it's got to cover. Oh, sorry, 20 billion galaxies we're going to be able to view, and they're going to be they're going to be imaged every
Right.
3 days for 10 years. So how many
Yeah.
times are they going to be imaged individually? And that is just 10% of all galaxies that we think exist in the
Yeah.
universe. So it's. I mean, I'm quite honest. I'm stunned. I don't know about
Yeah.
you. I'm
Me
really
too. Yeah.
stunned.
You
It'd be
know.
really. I mean, we had Gaia. We thought that was absolutely fantastic. The same sort
Yeah.
of thing,
Yeah.
but
Exactly.
on a different scale.
Yeah.
And that's only just closed down, and they're
Yeah.
still
Then
going through the data there.
then the what was the other one? European one.
But we got Euclid, haven't we?
That's the one you think that's on this.
Yeah, and again, that's mapping the dark matter in the
Yeah.
universe.
Yeah.
So once all this data comes through, I mean, it's going to be decades for them just to go through all the data.
That's right. Yeah.
And it is very well. It's magical times. I mean, with the Hubble, the Webb, and now the Vera C.
Yeah.
And I mean, we don't know really what the future is for all of these at the moment.
Yeah.
Due to funding matters, but that's
right. Yeah.
conversation to be had. Because one of
Hubble's linking on one gyro, isn't it? You know.
Yeah, literally.
Yeah.
And you know, with funding to keep these things running,
Yeah.
it's like I said, it's something for another conversation.
Yeah.
But I mean, it's like Sandra says here. It says, let me just pop Sandra's thing comment up. I mean, it says, imagine what else they are going to find. Exactly. I mean, this is amazing. I mean, when you combine all these space telescopes and now Vera, which is a terrestrial telescope, it's going to be absolutely amazing.
We just don't know what's out there, do you? You know.
Well, we don't know. I mean, it's nature, isn't it? Nature astonishes us every single time.
Yeah. That's right.
It doesn't play to any rules, or not any rules that we know. And this is why it keeps us guessing about, all this, the dark universe, as we say. We just haven't got a clue what's really going on.
I'm sure the data in these images is going to go a long way towards the dark matter.
Well, it's going to. All I can really say it's going to say to us is where it is.
Yeah.
But will it answer what it is?
Oh, I know. Yes. It'll still be dark.
Yeah, we still won't be able to see it unless we find some way of detecting this stuff. I mean, as well as dark energy as well.
We still won't know what it is.
No, and like I said, with dark energy as well, messing things up.
Yeah.
It's just very, very. It's fascinating times.
Oh, definitely.
The next couple of decades is going to go.
I mean, you think of the technology. think how technology developments in industry eventually comes down to us as consumers.
Yeah.
Just think of that camera. What is going to come out of? I know, obviously, the 32 billion pixels we ain't going to do it. You need a massive tripod then.
Yeah. Well, actually, no. Could give it 5 years, and that'll be pocket size.
Yeah. Yeah. That's right. Yeah. So yeah. Oh,
I mean, like you say, everything, all this technology comes to us. So
as a general photographer myself, it's just amazing that camera is.
yeah, it really is. I mean, and also seeing what it's done now, it's like you said, they've still got to tweak it.
Yeah.
I mean, I think it's totally amazing as it is.
It looks
Almost as good as a Sea Star.
Yeah. Very good.
But yeah, it's
I thought that one.
but it's absolutely stunning. I mean,
yes, it is.
What's going to come in the next few years once this thing starts rolling? And
Exactly.
I would just like to, when they get I mean, even if after a few nights and all that, I would just love to see whether or not are able to put together a time lapse, which will give us some indication. I mean, this is what we found with Gaia. I mean, Gaia was individual photographs, boom, 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 and then they used the data in the images to predict future movement of stars and everything else in our galaxy, and then they extended it to what was going on. And they built a video of that, didn't they? But that was a prediction video rather than actually live time things moving, which is, like I said, this is a time domain telescope.
That's right.
As I said, that's things that we can actually measure and see in real time. Anything that takes over 100 years basically is outside our scope, because not one person's going to be able to witness, well, maybe some people if they're lucky enough to witness that whole event. So I mean, I don't know, I'm gobsmacked. I don't know about you, Michael, but I really am. And with what, I mean, is it going to be like a James Webb and pose far more questions?
Oh yeah, I think it's. I mean, that's, isn't it? The more science questions that you answer, the more questions you get.
The more questions, the more you know, the more questions that come up. I mean, with James, like I said earlier on, I mean, with James Webb, we're beginning to question whether or not we know how old the universe is.
Oh yeah.
Because either our predictions are very, very wrong, especially about the size of galaxies and when they form, black holes, etc., which they're detecting now, huge spiral galaxies, which we thought shouldn't exist, but they're there so far back in time that does that mean the universe is older if our predictions are right, or are we totally wrong? It's because I think one of the main things they do want to know, and it was mentioned in the presentation, is the expansion of the universe. And can we understand what that phase change was when everything suddenly seemed to, so it was going along nicely, and then all of a sudden it accelerated. But look, recent, and as I did mention in the lead up, the recent investigations are probably predicting that the expansion slowing down and dark energy is becoming weaker. So again, let's say the more we find out, we got to reassess things.
And once it slowed down to zero, when it start going the other way.
Yeah, I mean, so I just want to pop this up. Sandra, trust me, I was not mocking the Sea Star. I've got one myself, and it's an absolutely amazing machine. In fact, I've been going through my some images I did a month or so ago because I haven't had time to do them. It's just amazing. Every time they bring out a new update, the things get better. So no, I'm not mocking it. Sandra, it's an absolutely fantastic machine. And once I get an equatorial mount sorted out, then it'll make things far much easier and far. I can just put it on, go to bed, and don't worry about it. But yeah, it's but yeah, it's ah man, I don't know.
I
It's
know, yeah.
I'm absolutely
Okay.
stunned. I don't know what to say.
No,
And the more and more images we see, I mean, most of these were just still images. I'll definitely be downloading the QR code
oh yeah,
and then start scanning them, because the first image they showed, up in the top right hand corner, there were 3 very large galaxies, and they
right.
were interacting. It
Oh,
was
right.
absolutely fantastic. I mean, you've probably seen it on the news. I think I've seen it
Yeah,
in the press and all that
yeah.
already. But yeah, there's 3 massive galaxies, and they're all interacting, and it's it's amazing to be able to see such detail. But those are galaxies that are quite close to us.
Yeah,
What's
yeah.
going on in the background, and once you start,
Oh, yeah.
I mean, what amazed me is when they were zooming in, the actual quality, the actual
Yes.
sharpness was
Yeah,
brilliant.
it was major all the way through, wasn't it?
It was. And as you like you said, you're a photographer, so it's you
It's just
can appreciate these things. I mean, I've done photography for years,
yeah.
and
I mean,
it's
I've got my sensor in my camera is a mere 47 megapixels.
I don't know what I've got in my Nikon.
Majority of uh, 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 DSLRs or mirrorless cameras are around 25, 26 megapixels.
Yeah.
And,
I mean, because when just for people who don't understand this, when we talk about the sensors, is these are little squares on
yeah,
a chip,
yeah,
and all their job is to collect light.
yeah,
So, and of course, they're mounted in a grid thing, and
yeah,
that's what they're doing. They're called light buckets. They're collecting light.
yeah,
So the more of them you've got, the more light you can collect. So
yeah.
the bigger the chip, or the more light buckets you've got on that chip, the
Mm,
better the image is going to be.
yeah,
So that's when we start talking about the chip size and the light buckets and things like that. And this is what's enabling Vera C. Rubin
yeah,
Observatory to see so far and in such detail.
yeah,
But yeah, it's absolutely fantastic. It looks like they're doing a question and answer session at the moment. We can go back and watch that a bit later on, because we're not going to sit here and listen to it. Oh, thank you, Sandra. That's very, very generous of you.
Oh,
We appreciate that, your donation.
oh, brilliant. Yeah,
And as we always say, any donations go straight back into the producing these shows.
yes.
Again, I apologise that there's few of us here. I apologise for my mess up earlier in the show when I dropped all my
Yeah,
notes, and then I had to try and sort them out.
that's like
So
podcasting does.
yeah, well, it was funny, but the actual loss of sound at the beginning of the actual show wasn't
Oh,
us. That was actually the people doing the presentation,
all right,
because I couldn't understand why I couldn't find any sound back and all that. And then all of a sudden
all
it
right.
just came up. They messed up a little bit. Yeah,
Okay.
but yeah, so that wasn't me. For a
Yeah.
change, it wasn't me.
Hey.
No, I just dropped my notes.
Yeah. All right then, guys. I'm going to go if you don't mind anyway. So,
No. I was just going to say we're just going to wrap this up. I
yeah,
just want to thank everybody who watched with us.
yeah,
We'll probably be talking about this tomorrow on the live show. Don't
yeah,
forget.
yeah,
What's it? 8 o'clock tomorrow.
yeah,
We'll be going live as usual. Come and join us. We'll be talking about other news, but I think the Vera Rubin will be the star of
yeah,
the
definitely.
actual thing, and also, of course, we'll be talking about the big explosion.
Oh,
If you know what I mean, yeah. And we'll probably discuss what that actually means for.
this
Um,
this Nova that's going on.
oh no! I'm talking about the one
Oh, the
yeah, the
Starship.
Starship. Yeah. Oh,
Starship.
there's a Nova, is there? Oh, okay then.
Well, I've heard something of it. I've got to look into it now.
Okay, then we're gonna have to find that. Get the C star right.
Yeah, yeah.
But
Anyway,
yeah,
Well,
Okay then, mate. Thanks for
Ross.
coming in anyway. It was nice to see you.
yeah, all right.
I'm glad you enjoyed Madeira. I
Yeah.
enjoyed Lanzarote, so
Yeah, good.
the best of it. Anyway, so we're going to wrap it up now, folks.
Yeah.
Thank you to everyone. Thank you, Sandra, for your kind donation. And we hopefully will see you tomorrow, where we'll be discussing this probably all night tomorrow. So this is absolutely fantastic, and it is a step forward. So
Yeah.
I'd just like to say bye for now, and we'll see you tomorrow. Keep
Yeah.
looking up.
Keep looking up.